Hi everybody, in today's tutorial we're just going to look at how to turn a little bit of theory into a practical computer program, okay? And the topic today is binary trees. Now the way binary trees work is we have nodes, and each node has a data item and a left pointer and a right pointer, okay? And if we want to search a binary tree for an item, let's say 9, then we look at the root pointer here, the root node, sorry. Are you 9? No. So then we need to make a decision about which path to go down. Is 9 less than 13? Yes, it is. So we go off to the left. Now we've reached 7. Is 7 equal to 9? No, it isn't. So now we need to make that decision again. Do we go left or right? Is 9 less than 7? No, it's not. Is 9 greater than 7? Yes, it is. So we come to the next node. Is the data of the current node equal to the search value 9? Yes, it is. We found the thing that we were looking for. So this is called traversing a binary tree. And in today's tutorial, we're just going to look at how to set up this scenario in a Python program. We will be implementing our binary tree on an array. Okay, so let's get started by developing the node class. So we'll design the constructor method, and every node object will have a data item, a left pointer, and a right pointer. And let's just set up some class variables. I'm not going to make them private. Let's just keep it pretty simple at the moment. And self.writeP equals writeP. Okay, so we've set up our node class. Now what we're going to do, let's use this as an example. We're going to set all this up as individual node objects. So let's have a go. The root node is a node object which has a data value of 13. It has a left pointer which points to the node at index 1. So let me try to explain that. If I was to put all of this into an array, I would put this at index 0, then going down and from left to right, this would be 1, index 1. This would be index 2. This is going to be index 3, index 4, index 5, index 6, and finally index 7. So that's how we're going to organize this in our array later, okay? So node 0's left pointer points to the node at index 1, and the right pointer points to the node at index 2. So there's our first node. Now let's make the next one. N1 is a node object which has a data value of 7 and a left pointer at index 0, 1, 2, 3, and a right pointer which points to the node at index 4. I'm just going to keep going. I'm going to bore you senseless as I develop my individual nodes. The node at index 2 has a data value of 18. It has a left pointer of 0, 1, 2, 3, 4, 5, and a right pointer of, that must be 6. The next node, N3, is a node object which has a data value of 5, and there is no left or right pointer. So I'm going to indicate that by using the value -1. There's no left pointer or right pointer. Okay, this is a leaf node. It doesn't have any child nodes. It's a leaf node. N4 equals node where are we? N4, 0, 1, 2, 3, 4, we're here. Data value of 9, and 0, 1, 2, 3, 4, 5, 6, 7. So the left pointer is -1, and the right pointer is 7. We've reached N5, which is a node. Which one is N5? 0, 1, 2, 3, 4, 5. It's this one. 16, and it's a leaf node as well. -1 and -1. And N6 is 21. And it has no pointers. It's a leaf node. And the final one, N7, is a node which has a data value of 11, and it's also a leaf node. Brilliant. Now let's create our binary tree by implementing it in an array. And is that right? We only go to N7, don't we? 0, 1, 2, 3, 4, 5, 6, 7. There we go. So this array here is kind of hosting our binary tree of nodes. Now, what we're going to do today, just to finish this particular tutorial, is just search for an item in a binary tree. So let's say the search item is, let's look for the value 16. Okay. And the root is at 0. And I'm going to make a search pointer and just set it to root. Okay, this is just my little habit. I like to set the root to 0 and not manipulate that in my algorithm. Just leave it at 0 unless it changes. So anything else can be set to root so we know where we're starting. Okay, now then, how are we going to go about this? While our search pointer doesn't equal -1, because if we're going through the tree and we reach a -1 pointer, it means we didn't find the thing that we're looking for. Okay? So while search pointer doesn't equal -1, and B tree search pointer dot data, the actual data item, doesn't equal the thing that we're looking for, which is our search item, these two conditions really need to be met. Why? If we just do this, what if the search item isn't in the tree? That's going to cause a problem, because eventually search pointer will become -1 and B tree -1 doesn't exist because -1 isn't a valid index in an array. That our program's going to crash. So to stop that from happening, while we're not yet at the end of the branch of a tree and we haven't found the thing we're looking for, let's do some processing. So what we're going to say is, if the item that we're looking for is less than the current data in the node, there we go, search pointer, B tree search pointer, so remember search pointer starts at 0, so we're in here, dot data is 13, so if 16 is less than 13, if the search item is less than 13, we're going to follow the left pointer. So we're going to update search pointer to be equal to B tree's current pointer, where it currently is, which is at search pointer dot left. So remember, search pointer is 0. If the search item is less than the data, then we're going to update the search pointer to be btree 0 dot left, which is this one. This will take us down to 1. Okay, so we're going to follow the left path. Else, if that's not true, there's only one other option. There are only 2 paths. Search pointer will update to btree search pointer dot right. And let's just come out of the loop. We're just going to put a bit of logic in here. If search pointer is the same as -1, it means we came out of this loop because this condition became false. So if search pointer is -1, we're just going to print item not found. Else, we can print item found at index search pointer. Okay, so we're going to look for 16. This is at index 0, 1, 2, 3, 4, 5. So let's run this program and see if we get item found at index 5. Grrr. Node takes no arguments. Node takes no arguments. Oh, I've just messed up my init. Let's run that again. Node has no attribute right. It's right P, isn't it? Left P and right P. Left P, right P. Let's run that again. Item found at index 5. So let's do 77. Hopefully this will be -1. Item not found. Item not found. Okay, so there's an algorithm for searching a binary tree for an item.